Hello, viewers. Welcome to episode 51, still on mechanic dynamics series that we are doing. We are getting to the end of this episode. We are picking the graphs of motion. We will narrow it to velocity time graph. And when we say velocity time graph, what are we referring to? We are referring to a graph that is plotted with time on the x-axis and velocity on what? The y-axis. So let's say we have, this is a graph. So this is going to be time with seconds, and this is going to be velocity as what? Meter per seconds in there. So this is the graph. So any lines drawn here describes some of the parameters we'll be talking about. So this graph can be used to find unknowns such as distance covered or distance traveled. You can also be asked to find the acceleration, to find time, to find velocity. Now we have to know that the slope, we know how to find the slope, the gradient. That's the change on the vertical axis over the change on what? The horizontal axis. Then that represents the acceleration. Remember, acceleration is what? Change of velocity over time taken. Then the area under the curve or the graph represents what? The distance traveled or distance what? Covered. So if we are to pick something like this, then this is passing through this place. Let's say I have 1, 2, let's say 1, 2, 3. Now, this is a uniform acceleration because the rate of change of every places, if I pick this side, the change here will be the same as this. If I draw it this way, so this could be whereby I have what? Acceleration equals to the change in velocity over change in what? Time. Whereby if I'm to have this as T1 and have this as what? T2, this will be V1 and this will be V2. Change between them will be the distance from here to here. That is going to be right away from here all the way to this place. That distance, that change. This is also from here to here. The distance between them is what we are calling what? Acceleration. So this is called uniform acceleration. And at this point, your initial velocity is what? 0. We are starting from here. That is a uniform acceleration. So the change we can have here, whether we draw a triangle here, smaller triangle, will give you the same answer if we were to draw the triangle at this point. That make it a uniform acceleration, a constant acceleration. And a constant acceleration is always a straight line. Now, we can also have another constant acceleration whereby we have 1, 2, 3, 4 v meter per seconds, t seconds itself. Then the line is drawn from here. It is also uniform acceleration, by here your initial velocity is going to be 1. So it is not always for it to start from the origin, but when you have your change on the vertical axis over the change, you still get the acceleration as what? The change. Here let me use the v over what? The t, which is talking about the acceleration. So this is more or less like a straight line graph. Finding the gradient. The gradient along this line, any 2 points you pick, the gradient will always be the same. Any point on the line satisfy that equation. So these two graph shows what they call uniform acceleration. But the acceleration cannot always be uniform. We can also have non-uniform acceleration. Let's see how we can represent when it is non-uniform acceleration. So let's see, we still have the graph of this nature where it is more or less like a curve. All we need to do is to find a straight line which will touch as a tangent to this and find our triangle. So this is also going to be the slope, which is the dv over what? The t, which is equal to the acceleration. Remember, this is going to be time in seconds. This is going to be velocity in meter per what? Seconds. Now, we can also have it in the sense that it will pass through this way. It will be uniform, stay this way, then it come down. let's see, we have the origin. So let me just say I have 1, let me have 5, let me have 7, I have here to be 1 and what? 4. I'm just labeling this V meter per seconds and time in what? Seconds. So this is also an example of what? Non-uniform. So we can say non-uniform acceleration. So this is non-uniform because the accelerations you find at each point is not going to be the same. It's going to be different acceleration. Here, the gradient at this point will not be the same as at top. So the gradient will be different, meaning the acceleration you find using this will not be the same. All right. Now, when we have this, from, let's say this is the origin, let's have the point X, they have the point Y, and have the point what? Z. It means there's a traveling from, this is O, not 0, O. The origin is 0, but this is letter O. From the origin, you move to X. From X, you move to Y, then you come down. So it means that we are going to have this complete graph representing the total distance being covered. So if that is the case, the first instance from here to here represents a uniform acceleration. You see it? A straight line. That will represent a uniform acceleration. Now, if we take this way, I think, let's make it a lot straight, okay? If we take this line, we can see that the velocity will remain the same. So at a constant velocity, acceleration becomes what? 0. So this is going to be 4 meters per second minus 4 meters per second, 0. Divided by time, even 1000, will still give you what? 0 as well, acceleration. So here, acceleration becomes 0. Then from here, you come all the way from 4 meters per second, you move down to 0, meaning you have reduced in velocity. That is retardation. That will give you what they call deceleration, right? So there are 3 parts of this journey. The first part, acceleration is uniform, is 0, deceleration, positive acceleration, negative acceleration, then 0. Now, remember the notes we have under, which talk about the area under the curve represent the distance what? Covered. So if I'm looking for the area, I can find the area of this, and find the area of this, and find the area of this. Add them together to represent the total area covered, which is going to be the total distance what? Covered. So let's represent this a little bit further and see. For what I have been explaining, from OX is representing uniform acceleration, XY represent a constant velocity or 0 acceleration, then YZ also represent a uniform deceleration. Let's iterate this a bit and see. Let's say we put this as 6 interval of 12. Let's say we have 0. Let's put 6, 12. Let's say we have 18, 21. So look at this. This is going to be a different diagram we are working with. Here we will be asked to find the acceleration at what? Each interval. So let's say we have to find acceleration. So the acceleration is what we are asked to find at each interval. Remember, we can use this to represent the acceleration at each interval. So from here to here, we can find the acceleration. So let's see, we have solution. So we are looking for acceleration at interval of OX. Remember, acceleration, I'll use A because of space, is going to be the change in what? Velocity. Right away from here, 0 to 12. That's the change in what? Velocity. Then, divided by change in what? Time. We can pick it 12 as final velocity minus what? Initial velocity. So we can easily say that this over this time taking, which is also going to be T1, T2. So as we'll be having 12 minus 0 remaining 12. Then 6 minus 0 remaining what? 6. Give you 2 meter per second what? Square. That is the acceleration at the interval OX. How about the second one? So the acceleration at the interval of x, y, we are having a equals to initial velocity from here will be 12, still 12. So we are going to have 0 divided by the time from here to here, going to be 18 minus this will give you 12 equals to 0 meter per second square. Remember, we mentioned that this is uniform acceleration. We mentioned that this is what? Constant velocity as acceleration being what? 0. So let's get the third one as acceleration. So at the interval of what? The yz. Still remember, your acceleration is going to be equals to the change in what? Velocity. You are beginning from here to here. You are now starting from here. Here you begin from 0, you end here. You get to this place, you start from here and move down. So this is the initial, as we can have here, and this is going to be what? The final. The final is going to be what? 0. So final, initial, I'll be having 0 minus 12 divided by the time. What is the time that you start your journey? You start from here. So this is the initial time. This is the final time. The distance between the two is going to be, I guess, 3, right? And that will give you 3 equals to negative 12 on 3, negative 4 meter per second square. The negative shows the deceleration. If you have negative, it means there is what? Retardation, slowing down, or reduction in what? Velocity. All right. So that is it for the first question. The second question, we can also be asked to find distance. The distance what? Covered. The distance covered is the area of this plus the area of this plus this. There are two ways of doing it. You find the area separately, or we use the trapezium what? Area formula for finding the area of what? Trapezium to find the total distance. So I'm going to find the area 1 because of space. I'll have area 1, which is going to be a triangle. That will be half base times what? Height. Height, base. From here to here, 6. From here to here, 12. So I'm going to have half of 12 times what? 6. And that is 36 meters. We are looking for distance, so let's put the meters there. Let's go for area 2. I'm doing all this because of space, but I'm sure you are getting the concept. This is a rectangle in here, going to be the length times breadth. What is the length? From here to here, interval of 12. From here to here, interval of 12. So I have 12 times 12, 144 meters. Let's go for the final area, which is going to be a triangle, half base times height. The base is going to be from here to here. That will be 3. The height will still remain what? 12. So half of this is what? 6. 6 times this is 18 meters. So total distance is going to be first 36, second 144, third 8. In total, this will give you 150, 180, 198, right? 198 meters as what? Total distance covered. If you are to use the trapezium formula, which is also going to be half A plus B times what? Height. A is the distance from here, which is 12. The B, the distance from 0 to here, 21. The height, still 12. When you multiply, you come back to the same concept. All right, the video is getting a bit longer, hence rushing of the earlier part of it, all we are trying to do is most questions will be based on the non-uniform acceleration structure, the particular one, where questions of this nature will be asked. So you can see the parameters you mentioned that you can be asked to find. One of them is what? Acceleration. We found it. Distance. You can also be asked to find what? The time. Taking into consideration velocity is what? Distance over time. So we can easily cross multiply and find the unknown variable. I guess concept well assimilated by you. Don't forget to come back as we take questions to text this particular part, and various aspects of questions can be dealt with. Like, share, comment, and subscribe.